Okay. We'll just continue with convex functions, and then we'll go into other concepts such as hyperplanes, extreme points, so on and so forth. But let's just look at a convex function, a function f like this. If you look at the set of points in the domain of definition of the function f, which consists of, if this set consists of those points whose function value is, say, less than or equal to alpha for some constant alpha. So here, alpha is a real number. This set is called a level set of the function f. Okay. Now I'm going to illustrate what it looks like in by means of a simple picture. But let's just first of all take the case of equality rather than inequality. If you look at the set of points x in the domain for which f of x is equal to alpha, a constant, what kind of a set is that? That's called a contour set, like the isometric lines in a contour lines in a geographical map. That's what you would see. They would be all of the same height from the sea level. And so with equality, that would be called a, so let me just make a, if this were equality, that would define a contour set. But with inequality, it defines a level set of value alpha. Suppose your function looks something like this in a domain AB. So my domain is the interval A to B. And this is my f of x on this axis. So you pick an alpha. For example, if you pick your alpha, let's call it alpha 1. Let's give a name to this set. Since it's a level set, let's just call it level set of the function f of value alpha. Let's just denote it by that. If alpha 1 is here, then is there a point in the domain for which f of x is less than or equal to alpha 1? The answer is no, because alpha is too small, and all the functional values are up here above alpha. For this reason, in this case, L of the function f of value alpha 1 is empty. There's nothing in it. Right? Okay. How about if alpha is here? Alpha 2. In this case, if you look at the height here, of course it picks up only the points in here. So if I call this, for example, point C, then L of alpha 2 of the function f is actually the interval from A to C. So you get the idea. Okay? If I happen to pick alpha up here, alpha 3, in that case, of course, L of alpha 3 is going to be how much? The entire interval from A to B. Because everybody, the value of the function is always less than or equal to alpha 3 because it's way up here. You see that, okay? All right, here's a theorem. So the theorem says if you have a function f which is defined on some convex set, on a convex set, S in the n-dimensional space, then every level set of the function is a convex set. First of all, before I go into the proof, do you agree with that? Well, to understand what's going on, it's always good to draw a picture and see what's really happening. So if we, before the proof, if we simply draw a picture to convince ourselves that that is the case, I draw a convex function, for example, like this, between, say, A and B. Okay? And then I look at a particular alpha, and I try to identify the level set. Well, you can see that the level set corresponding to that particular alpha is the entire interval that I marked here between, say, A prime, which is this point, and B prime, which is that point. So A prime, B prime is the level set of this function corresponding to that particular alpha, because it includes all the functional, well, all the points in the domain whose function value is less than or equal to alpha. Okay? All right, so you can see that it is convex indeed. Whereas if convexity were not really required for a particular alpha, you would have a situation such as this one, in which case, if this is again A, this is B, you would have this little section, which is the smaller part, smaller than or equal to alpha, and you'd also have this portion. So in this case, the level set consists of these two segments or intervals, closed intervals, and that's a disconnected set, so it's not convex. Okay? So it illustrates the basic idea here. So maybe we could use the picture as a proof. Does anybody see the light for the proof? The idea. How do I start? Well, when you know nothing about how to start, you just start. You start with the very basic idea. So let's just... So I'm going to write down the proof here. What am I supposed to do? So we just pick an alpha in R and consider the level set L of f of value alpha, the level set consisting of all these points x in the domain S, where f of x is less than or equal to alpha. So to prove that this set is a convex set, what do you need? You need to pick 2 points, arbitrary points. So let's pick x and y in the level set. And we also pick some lambda in the unit interval and consider the point lambda x plus 1 minus lambda y. What am I supposed to show? I'm supposed to show that any such convex combination is in fact in the set itself, right? That's the definition. So does anybody see if this is in the set or not? It is. It's quite obvious. We know, or the fact that x is in the level set implies f of x is less than or equal to alpha. And similar for y, f of y is less than or equal to alpha. Lambda being a non-negative number between 0 and 1 imply, together with these, that alpha, sorry, not alpha, but lambda f of x is less than or equal to lambda alpha. I'm just multiplying both sides. And that 1 minus lambda f of y is less than or equal to 1 minus lambda alpha. Again, multiplying the second inequality, which together, of course, implies that, what does it imply? That the point lambda x plus 1 minus lambda y, or the f value of this guy, is less than or equal to, what do we know about the function? It's convex. So we're using the convexity of f here. It's less than or equal to lambda f of x plus 1 minus lambda f of y. That's from the convexity, which, of course, implies, well, maybe I should put it here this way, less than or equal to the sum of lambda alpha plus 1 minus lambda alpha, which is alpha. Okay? Because this guy is less than or equal to lambda alpha, and this guy is less than or equal to 1 minus lambda alpha. So you just add them up, and that's it. All right, so these are simple things. But when you ask them in an exam, people come up with very complicated 5-page proofs. I have no idea how they do it. You know, try to look at problems in a simple way. Don't really think too wild. Okay? They are simple. Sometimes. Sometimes they are not. Okay. Okay, let's again consider the same function, some function with domain f, numerical function. And I'm now looking at the set of points. Well, actually, okay, this is incorrect. I'm looking at the set of points u. Let me put it this way. Yeah, let's look at the set of points alpha and x in the n plus 1 dimensional space. X is an n-dimensional vector, alpha is a number. Okay? I'm just referring back to the old notation. Okay, so such points where f of x is less than or equal to alpha. Now this looks a bit similar to what we had in the previous definition, except that this time alpha is also included in the vector of interest. So this is different. So what set is this? If your function is like this, for example, x is a variable point. It's a real number. And this one is your f of x. You pick an alpha. Then what do? You check those points that are less than or equal to alpha. In this case, I've got those points between these two marked numbers. Then I couple them with what? I couple them with alpha. So when you couple them with alpha, you trace this line here. When you change alpha to a smaller alpha, then of course you are looking at the points between these two inner segments, okay? And then you couple them with alpha, with that alpha, so on and so forth. So what am I generating here? What is the set under consideration in this particular example? Does everybody see? It's a line. No, it's not a line. It's a set. It's a set fatter than a line. Huh? Yes, somebody. I saw a hand there.
Is that the corresponding function?
No, it's not. It doesn't have to be. So alpha is not a fixed point here. In the other one, alpha is a fixed point. It's a fixed number. So you look at the subset of the domain, which gives you f of x less than or equal to that particular number. In this case, alpha is also a variable point. For example, is a point here. First of all, in this example, x is one-dimensional. But I'm in two dimensions here if I pick a point. Is this point in the set or not? Yes or no? Who said something? Somebody said something, but it wasn't clear if it was a yes or no. Huh?
I mean, if you put alpha accordingly, it can be in the set.
Well, I already have a point here that has, say, the coordinates alpha and beta. Alpha is this coordinate, and beta is this coordinate, or we call them something else, whatever you want to call them, UMV, for example. Okay? UMV. So is this point, in your judgment, in the set or not? What is U here? U is here. What is f of u? F of u is here. So is f of u less than or equal to v? That's the question you're asking. Is f of u in this? Yes, less than or equal to v. So you want to associate the f values with the second. Well, actually, I changed it around. So yeah, let's switch this around. Yeah, because otherwise it will be difficult. Let's switch it to that one. Okay. So is f of u less than or equal to v? The answer is yes or no? Yes, it is less than or equal to v. So that point is, in fact, in the set. Any point here will satisfy the same condition. Okay? So in this case, you're generating the set of points that are in here, on or above the graph of the function. Okay? If you're not convinced, work on it at home with a numerical example and see what's going on, because sometimes these things could be a little bit misleading. Okay? So that's the type of situation. If you reverse the inequality, you would be generating the set of points below the function or below the graph of the function. What is the set of points that are on the graph of the function? If I call it GF, they are the set of points, again, two tuples, U and V, such that V is equal to F of U. Which is the same set as U and F of U in 2 dimensions, where U is in the domain between A and B in this case. So we should also, I forgot that. Yes, we should also put the condition X is in the domain of the function. Why don't you add that? Without that, things will be ambiguous. Maybe that's why you weren't able to answer, because I left out an information actually. Okay? The set of points of the form U and F of U with U belonging to the set domain here. So here's another theorem. The theorem will say the following. If you have a convex function, then the set here is a convex set. So how am I supposed to state that? If F is a convex function defined on a convex set in Rn, then the set of points x alpha in Rn plus 1, where x is restricted to the domain and the condition f of x being less than or equal to alpha is fulfilled, is a convex set. Is the reverse implication true? If this set is convex, does that imply that f is convex? The converse is also true. In the other one, it's not. In the first theorem, it's not. The converse is also true. So, if this set is convex, then it sure implies that the function under consideration is convex. In the level set theorem, the converse will not be true. Can you give me an example for the level set? The level set will be convex, but the function itself will not be convex. For example, is this function, in your judgment, well, what are the level sets? If alpha is here, the level set includes the entire domain. If the alpha is here, the level set will be something like this. Okay? So you can see that any alpha greater than the marked point here will include the entire domain. Any alpha up to this one will include an interval. Any alpha below that line will give you empty level set. And so all the level sets are convex here. But the fact that the level sets are each convex does not imply that the function itself is convex, because this function is not convex. Okay? And in fact, if you look at the set here, you can see that that set is not convex either. So, you know, there are subtle differences between these things, which you might want to explore further when you're studying for the stuff. Okay. Well, unfortunately, this is not a course in convex analysis, so I'm going to stop there because I want to switch back to the linear programming context. So let's talk about now hyperplanes and half spaces. Let A be a vector in n dimension and alpha be a number. The set of points x in Rn such that A transpose x. Vectors are column vectors in my notation unless otherwise stated. So we're talking about the dot product of the row vector A transpose with the column vector x here. The set A transpose x equal to the number alpha is called a hyperplane with normal A. So A is the normal of the hyperplane. Now, this looks complicated, but when you actually look at examples, it becomes quite simple. Let's take, for example, two-dimensional space with A being the vector, say 1, 2. Pick a number for alpha. Let's pick it, for example, 4, whatever. Okay. Now, what set am I looking at? I'm looking at the set of points x in 2 dimension, right? Where A transpose times x, so x is your vector, say x1, x2. Okay? A transpose x1, x2 will give you x1 plus 2x2. That's what it will give you. That's your A transpose x, and you require that to be 4. That's the equation of a line. It's really simple. So that's your hyperplane. Okay? If you draw it, when x1 is 0, x2 is 2, which is here. When x2 is 0, x1 is 4, which is somewhere here. So your hyperplane is this one, going from the vectors, the points 0, 2, and 4, 0. Okay? What's the normal? The normal is 1, 2. Because if you go 1 unit this way, 2 units that way, you get this vector. And if you situate that vector, if you just carry it to some other point on the hyperplane, you can see that it's really normal. Normal means it's orthogonal, 90 degrees. It is indeed normal. Okay? If you have a 3-dimensional space, you would have a hyperplane such as this one. It would be a regular plane extending in all directions, of course. Okay? The normal of this would be this vector. It's a 2-dimensional vector, and it will be perpendicular to all the vectors that you can see on the hyperplane. So if you isolate a point x bar here, and if you pick any other point x in the hyperplane, so let x bar be a point in the hyperplane, call it h, which is by definition the set of points x in Rn, or R3 in this example, R2, sorry. R3 or R2? R3 in this example, for which A transpose X is equal to some constant alpha. This is also a given, okay? We know for every point X in the hyperplane that the vector A times x bar minus x, what vector is this? X bar minus x is it this vector or the other vector? Huh?
From x to x.
From x to x bar. So let's change it to, yeah, to make it agree with the picture, let's just do it this way. X minus x bar, which is this vector. Now I'm writing down my stuff like ants. Maybe you see them, maybe you don't. But anyway, it's x minus x bar. How much is this? This is 0. The reason is A transpose x minus A transpose x. Each one gives you alpha because each is on the hyperplane. And of course, that outputs 0. That's why A is perpendicular to each such vector. There's a reason. Okay? So. What's a hyperplane in one-dimensional space? A point, yes. So if your A vector, if your vector A is a single number, then you get a point for your hyperplane. That's the way, if you just write down the definition, this is the way this is the way the set is defined, which is of course nothing but the point 2. It's just a single number, okay? That's your hyperplane. Okay. A hyperplane H with normal A defines two half spaces. One of them is the set, so if I call it HS1 and HS2. One of them is the set of points X in the same dimensional space such that A transpose X is less than or equal to alpha, where alpha is the defining number for the hyperplane. The second one is the set of points X in Rn such that A transpose X is greater than or equal to alpha. Okay? So in the previous example, for n equals 2, if your hyperplane is like this, with normal perpendicular, say going this way, then you've got one half space here, the other half space is here. Okay? Each half space contains the line as well. Which one is which? Which one is the less than or equal to 1? Are you sure? I don't know. You can figure that out. Okay. Okay. It might depend on also alpha, or does it? Huh? Yes, yes, good. Points here are in the same direction as A, or they are within 90 degrees of A. So which part is this? A transpose X greater than or equal to alpha. This part is the set of points X which are less than or equal to alpha. Yes. Okay, let's see what else we have here. Another definition. A set S defined by the intersection of finitely many hyperplanes and half spaces in Rn is called a polyhedron or a polyhedral set. If a polyhedron is bounded, meaning that if it can be contained in within a sphere of finite radius, bounded means that, okay, then it is called a polytope. If each hyperplane and half space that defines a polyhedron contain the origin, then such a polyhedral set is called a polyhedral cone. So it is called a polyhedral cone. So let's just draw some pictures. Well, I'm out of black pens, so I'm going to write it in blue. Let's take the case of 2 dimensions again. First of all, in 2 dimensions, things will look like this. So this line is one half space. It defines a half space this way. This one also defines another half space. What half space is this? The set of points x1 is greater or equal 0. So what is the normal here?
1, 0.
Yeah, 1, 0. x1 greater or equal 0. The normal is 1, 0. See? Okay. This one is the set of points for which 0, 1 times x1, x2 is greater or equal 0. That one, that's what that one defines. And then let's also have this one and this one. And if you look at the intersection, of course, that's what you get. That's a polyhedral set. That's what it looks like in 2 dimensions. So this is a polyhedral set. Is it a polytope? It's a polytope, okay, because it's bounded. Is it a cone? Let's just a second. We should not include the half spaces here. Yeah, why don't you erase that? If each hyperplane that defines a polyhedron contain the origin, then it is called a polyhedral cone. This is wait a minute, this is not really what I want. How should I say this? Let's put it this way. Let's revise this definition because it doesn't quite convey the meaning I have in mind. If the defining hyperplane for each hyperplane and each half space that's what we mean. All right, so if the defining hyperplane for each hyperplane, in this case, the defining hyperplane for a hyperplane is just itself, and the defining hyperplane for each half space is just the hyperplane portion of the half space, the boundary, okay? That defines a polyhedron, contains the origin, then it is called a polyhedral cone. So if you want to give an example for that, I've got 4 half spaces here defined by each of these lines. I might also have another one passing through the origin and going this way. So we've got 5 half spaces under consideration. If you look at the first half space, which is the one defined by number 1 hyperplane, the defining hyperplane for that is the set of line is the line that you see in the picture. The defining hyperplane for number 2 is this one. Okay, so on and so forth. So each defining hyperplane passes through the origin. What is the polyhedral set under consideration? It's this one. I'm running out of ink today. It's this one. So that's the polyhedral cone in this particular example. Okay? You might want to reword the definition according to what I demonstrated, because this is not really in good shape. Whatever, it seems to convey the meaning. Why do we worry about these sets? If you look at the feasible set of any linear programming problem, of course, a linear programming problem has a bunch of constraints, and you're interested in a set of points that satisfy all constraints at the same time. Okay? Now, each constraint, if a particular constraint is equality, the set of points that satisfy that equality will be a hyperplane. If a constraint is, say, less than or equal to type or greater than or equal to type, then the set of points satisfying that particular inequality will be a half space. So you have a bunch of half spaces, and since you're looking for feasible points that satisfy each constraint simultaneously, you're looking at the intersection of half spaces and hyperplanes. Okay? So, such an intersection is a polyhedral set. Now, how does that relate to convexity? Does that look like a convex set to you? It is. It does. Right? It's a convex set here also. So, a linear function is a convex function if you just apply the definition. And when you look at half spaces, such as defined by this expression, this is the function value, that's alpha. And you're looking for a set of points x that satisfy that. What set is that? Level set? It's a level set of that function of value alpha. And what do you know about level sets for convex functions? A linear function is convex, so its level sets are always convex. So the intersection of level sets will also be convex. Did I prove that? The intersection of two convex sets is convex. We proved that, right? And you can extend it to any number of sets, actually. The intersection will be convex. And so that's why we're worrying about these things. I guess we're out of time, so that's it for today. Hatice will solve you some problems, okay?